Hey, hi. Welcome to Navie class part two. Let's get started. So, in this lecture, we'll go through what is Laplace smoothing and what is different types of Naive Bayes and implementation using scikit-learn. Okay, so let's get started. So, what is Laplace smoothing? So let's say during testing, we got sentence like this book is excellent. So now we have to calculate probabilities for that, right? Like we'll go through each word and we'll see how many times it occurred in the positive review and also in the negative review, and we'll multiply all those words probabilities, and then we'll decide which one has the highest, whether it's a positive review or a negative review. So let's say we have probability for this. It occurred two out of six words. Let's say in the positive review, and book occurred one word occurred one time. Okay, and six out of six words, and let's say is occurred three out of six words. And but the problem is excellent. This word is not there as part of training, so it will be 0/6. Correct. Now what we'll do, we'll multiply each word probability, right? So 2/6 into 1/6 into 3/6 into 0/6. Since this extent has never occurred in the training sentences, it will be 0/6 and everything will become zero, right? This is not what we want, right? Because by just this error, like where excellent is not there in the training data, everything is becoming zero. So in order to overcome that problem, people came up with something called as Laplace smoothing. So what they're trying to do is, instead of not just giving 0 divided by 6 as that everything become 0, and if you multiply everything the result will be 0. So they just add something called as 1 to the denominator numerator. So we'll add one every count, so it's never zero. So they will add one to the numerator for every word, not only just for extent, for each, book, and this. So it will be 2 plus 1. And 2, since we are adding 1 at the numerator, right, in order to balance it, in the denominator, what we'll be adding is, along with 6, we'll be adding how many unique words were there across the data set. Across the data set in the sense, both positive and negative reviews. So the 6 that we are looking at is number of words in positive review only. Now what we need to do is, along with that 6, we'll have 6 plus 8. So 8 here refers to all the words, that unique words that were there in both positive and negative review. So now let's see what happens to the extent word now. So it will be probability of, so since it never occurred, so it will be 0 plus, we are adding 1 to the numerator divided by 6 plus 8. 8 is like unique words across positive and negative reviews. So that will balance out this one, so that the division will never be greater than 1. Okay, so this is called as Laplace smoothing. So just remember that what is Laplace smoothing. Sometimes you may not see, during testing you may not see a word that is occurring in the training, so that if you just go with normal approach, everything will become zero. So in order to overcome that problem, people came up with the Laplace smoothing, so that you will add some 1 to the numerator divided by, since you are adding something at the numerator, you have to balance it out. So you will add in the denominator like unique words in the whole corpus, like in the both positive reviews and negative reviews, right? So that's why you are seeing 8 here. So let's say 8 is the total number of words, unique words that were there in both positive and negative reviews. So that's how Laplace smoothing is applied. Now let's look at different types of Navy bias. So first one we'll look at is something called as Gaussian Navy bias. So Gaussian Navy bias implements the Gaussian Navy Bayes algorithm for classification. So when do we use Gaussian Navy Bayes? So you will be using Gaussian Navy Bayes if the features that you have are normally distributed and those are continuous, right? So let's say if this is the data that you have. So the idea of this data is that you will have sepal length, sepal width, petal length, and petal width of a iris flower. Then based on these features like sepal length, sepal width, petal length, and petal width, we need to identify what type of species that plant belongs to. Either it is setosa, or it is virginica, or it's versicolor. So there are three types of classes. Either this plant, given this sepal length, sepal width, petal length, and petal width, You need to identify which type of species it belongs to, either Setosa, Virginica, or Versicolor. So this data looks like a tabular data, right? And it's like a continuous data. Like every feature is a continuous feature. So this is a perfect example where you need to use Naviebase, Gaussian Naviebase specifically, because it assumes that features are continuous and also assumes that features are Gaussianly distributed. So what is normally distributed? I hope you remember it while you're studying it in your BTech. But if you don't remember it, that's fine. When we go through statistics and stuff, we will know what is Gaussian, what is normally distributed, what is skew distribution, and all that. But now assume that you will use Gaussian Naviebase when the futures, right? The futures are continuous and those should be normally distributed. If those are not normally distributed, you convert those features first to normally distributed data, and then you will use Gaussian Navier-Bayes algorithm. Okay, so that's where Gaussian Navier-Bayes is used. So next type is multinomial Navier-Bayes. So mostly multinomial Navier-Bayes is used when you are dealing with the text. So like text classification. So given a review, you need to find out whether it's a positive or a negative review. So when you're dealing with the text, usually multinomial Naive Bayes comes into the picture. So mostly you can relate to this formula. That's what I think we used mostly in our explaining of Naive Bayes. So you will see how many times that word occur divided by uh, particular class number of words that particular class has, and we talked about Laplace smoothing, right? So you will add alpha divided by alpha into n. So alpha can vary, but mostly it will be if you are using Laplace smoothing if alpha equal to 1, and n, as I mentioned, it's like unique words in the whole corpus, right? So that's about multinomial Navier-Bayes, and usually you will use it when you are dealing with futures that have frequency. So frequency in the sense like you should have some numbers. It may not be continuous, but it's like a categorical numbers like 2, 3, 4, 5, 6, or something like that. So mostly when we have seen the example of positive or negative reviews, right? We have that count like number of times a word occurred, 2 by 6, 5 by 6, or something like that. So when you're dealing with that frequency or count of a particular feature, you will go with multinomial Navier-Bayes. So it mostly used when you're dealing with text data, like when you're using TF-IDF for bow vectors. So don't worry about those bow and TF-IDF. We are having a NLP course where we will be explaining all that. So this is just to give you a touch about how you can implement an algorithm by just using some 10 lines of code. So we'll go deep when we look at the other when we cover the other chapters like statistics and all that. Okay. So the next one is about Bernoulli Navier-Bayes. Okay, so Bernoulli Navier-Bayes, you will use Bernoulli Navier-Bayes when you are dealing only with one or zero kind of features. So you don't have count, you have only features that say either it's a one or a zero, right? In multinomial Navier-Bayes, you will have frequency, like you will have 2, 3, 4, 5, 6, something like that. But in Bernoulli Navier-Bayes, you will just have either one or a zero value for all the features that you have in your data set, right? So let's take an example for when to use Gaussian Navier-Bayes. So as I mentioned, this is Iris dataset. It's like a hello world for data science. So you have set sepal length, sepal width, petal length, and petal width, and you need to identify which class category that flower belongs to by giving these four different variables. So now we'll separate the data sets into like target variable and futures. So here our target variable is species, right? We need to identify, given a data, which of these three classes it belongs to. So what we will do, you usually drop the ID, which is not necessary. It doesn't give us any information. So we need to, using pandas, we will drop ID column data and class data. So when you are training the model, right, you should not see classes, class labels. You should see only the features, but not the class those features uh, belong to. Like when you're just dealing with that during testing, you should not see. But in during training, we are just dividing those into futures. What are the futures that we have, and what are the target variable that we are interested in, right? And then we pass this data to training and test sets. So we'll import something called as train test split uh, from sklearn, and we'll just pass x and y. So x contains futures and y contains target variable that you are interested in. So during training process, you know what is the input and what is the output. But in the testing process, you will only have input but not output. Okay. So here we are just passing saying x. X is nothing but all the input data. Input data is sepal length, sepal width, petal length, and petal width. And output data is y, which is class. So whether it is a Setosa, Virginica, or Versicolor, and we are giving test size as zero point 0.3, saying that if there is 100 data points, so 70 data points will go to train and 30 will belong to test. So what is train data and test data? So train data, in the sense, you will give the train data to the model so that model can learn, and you will test it on test data to know how well the model performs, how well it learned during training, so that you know how well it performs during the testing. So in order to do that split, so we'll use this train test split. We'll pass the input data and what is the output for that input data, and you will set test size equal 0.3. So it will divide training data as 70% and 30% belongs to test data. So by just using these two lines of code, we are just importing Gaussian Navie bash. So scikit-learn.navie bash import Gaussian NB, and you will just say Gaussian NB, Navie bash equal to Gaussian NB, and you will say Navie bash dot fit. You will just pass input data and what is the output data. So X train and Y train. So this is where training happens. All the logics that we are looking at, like going through each word, we'll see how many times it occurred and all that. So usually that everything happens by just using that fit function. So all the core logic automatically happens when you just use dot fit function. In the background, everything, all the algorithm and everything gets run by just taking the input and the output. So once the model is done, when the training is done, you can just start predicting. So you can just pass X text. So you can just pass input data and it will able to predict, right? Then if you want to know how well it perform, let's say if you are interested in accuracy score, so we'll just say accuracy score, Y test and predictions. So Y test is the actual data that you have for test, and predictions is something that model had predicted. So we'll compare both and to see how well the model performed. It says that model was good at, like, it was accurate 93%. So it did some miscalculations. It's around 0.7%, but 93% of the time it was correct. Don't worry about this metrics accuracy and all that. We'll learn it as well in coming lectures. So for multinomial naive, as I mentioned, we usually deal it when we have text data. So let's say we have some feed data and we need to find out whether it's a positive review or a negative review. So positive review is labeled as 1 and negative review is labeled as 0. So since, and we'll just dividing data into input data and output data. So X contains all the input data and Y contains all the output data. So here input is only text, right? So we just add to it and everything will be in max, and we are interested in this label column, so y will have label data. So train test fit again will divide into 70 and 30, and we'll use something called as count vectorizer. So just to, it will help us to count what we did previously, right? Like how many times this word occurred in given review and all that, that all countings and everything, you can just use count vectorizer to do that. Don't worry too much about it. We'll learn as part of NLP, like how it works internally and all that. So as of now, just remember that count vector will help you to count whatever we are doing manually, right? Counting how many times a word occurred and all that. It will do it automatically. It will create a vocabulary like, okay, this is number of times this word occurred and all that. Then you just need to import multinomial navibas, and that's a fit training data and y train. So this training data comes from this count vector. Okay, and that's y train is the actual labels. So automatically in the background all the calculations happens, and when the model is ready, you can start predicting by passing testing data. You'll have predictions. If you want to know how well your model performed, you can just say y test and predictions, and you will get the score. It was accurate about 90%, classifying whether a review belongs to positive or a negative review, right? Cool. Same for Bernoulli Navigas. We'll also use text data here, and you'll same process what you have done in you know uh, multinomial Navie. So we'll divide the data into input and output. We'll pass it to train test fit, divide into 70% training and 30% testing. And we will use count vectorizer to count and just import Bernoulli NB, just say fit training data, y, y train, original levels. And we will start predicting by passing testing data. And the score was around 88. So you can see there's a difference. So multinomial is around 89, but this is reduced to 88 because we are counting, right? So usually when do we need to use Bernoulli Navier? We only need to use when futures are either 1 or 0 kind of data, binary data. But here, since we are using count vectorizer, we'll have that counts like it would occur like 3 times, 4 times, or 5 times in the corpus. So it's usually, so when you're dealing with that kind of data, then you need to use multinomial but not Bernoulli. So you use Bernoulli when it is only your input data is either 1 or 0. Okay, so don't worry if you don't understand anything here. It's just to tell you like how easy is to use these algorithms and stuff. In coming lectures, we'll go through deep and understand each and every line and what's happening inside it and stuff. Okay. So we are planning for an NLP course. Maybe it will be starting from next week or so. We're preparing all the lectures and all that. So it might be ready by next 1 week or 2 weeks. I will let you know once it is ready. So there, I think we'll go a little bit deep on each algorithms and all line by line, and we'll see what's happening over there. Okay. Yeah. Thanks, everyone.